Good morning, everyone. You're welcome to today's lecture. We'll be talking about Ohm's law and analysis of direct current circuits containing resistors. So Ohm's law is obtained from experiments, and the experiment is what is the diagram for the experiment is the figure we have here, and it shows a voltage source, which is a battery, connected to a resistor. Then the A is an ammeter, V is a voltmeter. As you've learned in secondary school, ammeter is used to measure current flow, while voltmeter is used to measure the potential difference of, across a particular component, or the voltage across a terminal or EMF of a battery and the likes. So in short, ammeter measures current, voltmeter measures voltage. So if we ignore the meters and have our circuits to be in this form, where we have a battery connected to a resistor, we would expect currents to flow in this direction. You would notice that in this case, the positive terminal in batteries is higher than the negative terminals, unlike in capacitors where the schematic symbol is represented by two parallel lines. In this case, also by two parallel lines of the same length. In this case, fine, there are two parallel lines, but one is higher than the other, meaning that the potential of one is greater than the other. And current will flow because there is a change in potential difference. So in this case, when we connect a battery to a resistor, current flows. So what amount of current flows? That is what Ohm's law is telling us, which is that the current that will flow through a metallic conductor depends on the voltage, directly depends on the voltage across the metallic conductor. And that is the voltage across the metallic conductor is V, while the current flow is I. And then we have a constant of proportionality R, which is the resistance. So conductors, which are known to be good carriers of electricity, that's materials that permit electric flow, flow of electricity easily, they obey Ohm's law. And we have different types of conductors anyway. There are some that they obey Ohm's law, and some they don't. Not that they don't, but they don't directly. When we are talking about Ohm's law is telling us that the voltage, when we plot the voltage and the current, we should have a graph that looks like this. But there are also some, so if we have a material in which, as we are increasing the voltage, the current flow is increasing linearly, then we will say such material is an ohmic conductor because it obeys Ohm's law. But there are also some materials in which when you plot the graph, you are going to have, so this is for ohmic conductor. And there are also some materials that are non-ohmic. When you plot the graph, you can have something like this. So since it is non-linear, the relationship between the voltage and the current flow is non-linear, then we'll say it is non-ohmic. So these non-ohmic materials are popular with semiconductors, where there is no, where the free electrons are not as much as we have in conductors. So when we spoken about current flow through a conductor depending on the supply voltage. But there is a property that is constant. Well, we said V is directly proportional to I. V equal to I with constant R. V equal to IR is the popular Ohm's law. This property R is the resistance. The resistance gives us, just like the name resistance, tells us, it's a property of a material that tells us how much opposition it gives to current flow. It tells us how much opposition it gives to current flow. So that means that a material with high resistance would prevent current from flowing, or will oppose current from flowing, to give a bigger opposition to current flow compared to another material with small resistance, just like the English word resistance, the ability to resist. So materials with very low resistance are good conductors, while materials with very high resistance are not conductors, they are insulators. So materials with whose properties are in between, they are called semiconductors, or we can also say poor conductors. And we also have some materials that do not oppose current flow at all. That means they offer zero resistance to a current flow. Such materials are superconductors. Though currently we don't have anyone that would conduct at room temperature, but at very low temperatures, some materials conduct electricity with no resistance at all. So they are superconductors. So when we, in our previous topics where we spoke about electric charges, I made mention that electrons are the major participants in electricity. And one of the reasons why that should be is because electrons are lighter than the protons. And since electrons are lighter, they are more mobile. They can move easily. They can move more freely compared to the protons. In fact, they are about 1,800 times lighter than the protons. So they are more mobile. And even that should be why the name electricity resembles the name proton, resembles the name electron. The name electricity looks like the name electron. So electrons are the major participants in electricity. So when we have a circuit, for instance, this is a battery. This is the positive terminal. This is the negative terminal. Electrons are negatively charged. Electrons are negatively charged. We expect them to flow out of the negative terminal of your battery. So in the circuit, electrons flow, and they flow from the negative terminal to the positive terminal. But it is not easy to think about something that is negative to be a major participant, or to be a major carrier. It is easier to think about something positive when you are trying to do some analysis than to be talking about something negative. So for that reason, we have what we call the current flow, which is usually represented as I. So it is not just current, or the full name is conventional current. Conventional current. Conventional current because it is more convenient to think about currents while analyzing circuits than thinking about electrons. So when we say current is simply the rate at which electrons flow through a particular cross-section. So, but for easy analysis, the direction points from positive to negative. So we'll just forget about electrons for now, and we'll think about current. We'll think about current as that positive-like carrier that flows out of the positive terminal down to the negative terminal of your battery. So when we are talking about electric circuits, why do we need electric circuits? Because we want to use the electricity to perform some work. Easily, we can at all times draw a battery, connect it to a resistor. But this resistor, what is this? At least we know this to be the battery, or we know it to be the energy source. Then what is this resistor? The resistor is the load. It can be your pressing iron, it can be your hot plate, it can be your ceiling fan, it can be anything. So as long as it takes electricity and use it to perform some functions, then it can be represented with a resistor, at least for now. So the basic circuit elements we'll be using for now, for this class, will be battery, cell. We've seen battery. Cell is just a smaller unit of the battery. Combination of cells gives a battery. We've seen resistors. Another way to represent resistor is doing the zigzag line. And to measure currents, we've seen the ammeter, and we have seen the voltmeter in the experiments by Ohm. So if we would add more, we've seen, and later on we'll be seeing inductors. So if you will come to So let's talk about an application of Ohm's law. This is a simple circuit comprising of a battery and a lamp. This lamp can be said to be the resistor. What is it doing? It is converting electrical energy to light energy, no? Okay. And it's not just light energy, it's also the amount of light is not, it converts, the electricity it converts to light is not 100%. Some part of the electricity is converted to heat energy. So now the question is saying, what is the current flowing through the lamp in the circuit? We know the voltage to be 12 volts. We know the resistance to be 3 ohm. What is the current flow? So the current flow here will be from Ohm's law, which says V equal to IR, then we can have I to be equal to V over R. Then I will be 12 over 3 ampere. Or if you like, it's 12 volts over 3 ohm. And that will give us 4 ampere. So I would like us to look at this diagram before we move forward, because when the brightness of this bulb depends on the current that flows through it. When we want larger currents to flow through this bulb, we can increase the voltage of this supply so that larger currents will be able to flow, because V is directly proportional to I. If we replace this bulb with another type of bulb, if we maintain this the battery to be 12 volts, and we replace this bulb to another type of bulb, which is of the same nature, but of a lower resistance. If it's of the same nature, that is made of the same material, but the resistance is lower. When the resistance is lower, larger current will flow. And when large current flows, then we'll say that we would expect the bulb to be brighter. So we would expect a bulb of 2 ohms to be brighter than that of 3 ohms if they are made of the same material and they are connected to the same voltage source. So let's continue. Okay, so when you check your different, our holding this tungsten bulbs, which is now holding this, you must have seen some to be 60 watts, some to be 100 watts, some 200 watts. What that simply means is that those that are rated 60 watts have higher resistance compared to the ones that are 100 watts. That means that the ones that are rated 100 watts will be brighter than the ones that are 60 watts. The ones that are 100 watts will be brighter than the ones that are 60 watts. But larger currents will flow through that of 100 watts, meaning that the ones of 100 watts have lower resistance compared to the ones that are 60 watts. So let's move forward. So I've said earlier that for currents to flow in a circuit, there must be change in potential. Just like for an object to drop in space, it should drop from, there must be change in gravitational potential. The same thing happens, and as we have also said while talking about motion of charges, we said charges move from place of within different potentials. When we're talking about the work done by charges or work done by charges, we were considering the potential of the previous point and the potential of the current point. So the same thing applies for, since current flow has to do with the movement of charges. Since current flow has to do with the movement of charges, then for currents to flow, there should be change in potential. For currents to flow, there should be a change in potential. That is, there must be a potential difference, at least across the resistor where you want the current to flow through. So when your battery is not issuing out any current, when your battery is not issuing out any current, and you measure the voltage across such battery, what you are measuring is EMF. When you have your battery, it is not issuing out any current, and you connect your voltmeter across it, what you are measuring is EMF, electromotive force. By the time you begin to connect resistors to your battery and the current begins to flow out of your battery, the voltage you measure here would reduce. The voltage you measure will reduce. So when you connect a resistor R to your battery, the voltage will reduce. So when no current is flowing out of the battery, what you measure is EMF. So, but in most of our examples, you would not notice any reduction in voltage whenever you connect another resistor. Let me give some examples that you should be conversant with. You must have seen different batteries in the market, Tiger batteries. some are slim. For calculators, wall clocks, some are a bit fatter. Also, you must have seen some generators. Some are small, some are industrial size. And you notice that this small battery is rated 1.5 volts. The big one is also 1.5 volts. The small Tiger generator is rated 220 volts. And there are also some big generators, 220 volts. By the time this small battery begins to issue out current, the voltage would reduce. It may be small, it may be large, but the voltage will reduce. And the reduction of that voltage has to do with the efficiency of that battery. And the reason why the electrical explanation for why the voltage is reducing is because the battery has something that is called internal resistance. Internal resistance. So because of the internal resistance, so a voltage source that has small internal resistance is said to be very efficient. Ideally, in most of the circuits we'll be looking at, in most of them, we will not be talking about their internal resistance. We'll be assuming that the internal resistance is 0. And in such cases, the current that flows out of the battery, even if it is very large, the voltage will still remain its voltage. So like I was saying, when a certain current, let's say 1 ampere is flowing out of this battery to, let's say, to a bulb. Let's say it's connected to a bulb. Let's say 1 ampere is flowing out. And because 1 ampere is flowing out, when you connect your voltmeter here, it drops to 1.4 volts. If you connect the same battery to this, if you connect the same bulb to this big battery, the voltage may drop to something like 1.45. So whatever that this has dropped to 1.45 volts means that the internal resistance here is smaller than what we have here. And also, when we use the same analogy for your generator, at least you must have noticed with the small, common small generators we use at home, when you put on the bulb, fine, it makes a sound. When you put on the fan, it complains. When you switch on another fan, it complains further, and the brightness of your bulb begins to go down. That's one of the things that happen that you don't put cognizance to. And when you switch on the pressing iron, it goes off straight away because you have overloaded it. Whereas all the load for your everything in your house and that of your neighbor's house and the whole streets, a big gen will carry everything and would still be smiling. Whereas we are still talking about the same 220 volts, 220 volts. The reason is because this is having a smaller internal resistance. It can issue out larger amounts of current without a reduction in voltage. So we'll also be talking about this later on when we are talking about magnetic fields. But I just want to point out to take out is that when we are talking about current flowing out of the voltage source, when current flows out of a voltage source, the voltage from that source reduces. It is only in ideal situations where the internal resistance is 0 and current flows out of the battery without a reduction in voltage. So that is, when we say a battery, when we say battery, in reality, in ideally is this, but in reality, it is attached to a small R So we can say this is the original schematic of a battery. We can say this is the original schematic of a battery, where it is connected to its internal resistance. Then after this, we now start talking about it being connected to something else, maybe a resistor, another resistor. So let's move ahead. So we can connect resistors in series. When we say resistors in series, the order will be in this form. That is, the ends, the right end is connected to the left end of the second, the right end is connected to the left end of the neighbor, and that's in this manner. And that means that when you connect this to any particular source, the current that flows into R1 will flow through R2, through R3, and through R4. So this can be likened to be like when we talk about our wires, which are conductors, they carry electric current. We can think about them also to be like a pipe of water that carries, like a pipe of water that carries water. And in between, we have some blockage that offer resistance R1, some blockage that prevents free water flow all through the water pipe. So when water is flowing, it experiences some hindrances on the way. But whatsoever water molecule that goes through this part will also go through this part, So the same volume of water that flows through this part per time, the same amount of water that flows through this point per time flows through each of the points per time. So that is how resistors in series, that's how they work. So the point to note here is that when resistors are in series, the same current flows through them, and the total resistance R is equal to the sum of the individual resistances. So when we have 4 resistors here, the total resistance will be R1, R2, R3, R4. So let's say each of them are 1 ohm, 1 ohm, 1 ohm, 1 ohm. Then we can replace all of them with a single resistor. That will be 4 ohms. Or let's just say R1 plus R2 plus R3 plus R4. You can replace them with a single resistor whose resistance is a summation of R1, R2, R3, and R4. So we can also have resistors. So you can see R1, R2, R3, R4 here is the same as the R1, R2, R3, R4 we have at the lower corner. Here. So for the fact that it is bending, at least our water pipes also bend. The same water flows at the same rates. Even if it is bending at different cross sections, water flow will still be the same all through the pipe. So the same thing applies here. So these are in series, even the fact that it's bending. And let's move to another type of arrangement. In this arrangement, it's called parallel. All the left ends are connected together, while all the right ends are connected together. So when current is flowing in this from the left, it enters this, gets to this junction, it splits into 4. So parts of the current will flow through R1, another part through R2, another part through R3, and another part through R4. And the 4 branches will come to meet at this point. So the 4 in the four parts, just like they've met, is the same way that the currents that flowed through each of these resistors would also meet here to continue in this direction. So, and one point to note here is that the potential difference across the resistors are the same because their left ends are joined together, their right ends are joined together. So when we say the potential across R1 is 2 volts, when we know the potential difference across resistor R1, then we know the potential difference across the 4 resistors because they are in parallel. Unlike what we have in series, the voltage drop across R1, voltage drop across R1, when we call it V1, when we call the voltage across V2, the voltage drop across this, when we call it V3, the voltage drop across, when we call it V4, the total voltage here will be equal to V1, that is the total voltage across it all this way, will be V1 plus V2 plus V3 plus V4. But the current that flows through R1 is equal to the current that flows through R2. So I here is the same. I1 is equal to I2 equal to I3 equal to I4 equal to I. That is what's obtainable when we have resistors in series. But when we are talking about resistors in parallel, the current that flows through I1 plus the current that flows through I2 plus the current that flows through I3 plus the current that flows through I4 add up together to give us the total current. Maybe let's I total. So let's say current I total is flowing into this group of resistors. It splits into different currents. I1 will flow through I1, I2 will flow through R2, I3 will flow through R3, I4 will flow through R4, and they will come together, meet at this point to add up again to I total. So the I total that flowed into this junction will be the I total that will flow out of this junction. So, but the different currents will flow through R1, R2, R3, R4. Different currents in the sense that we are not sure about their resistance. If the resistors have the same resistance value, then the same current, then we will flow through them. Not the same, not really the same current, but they will be divided. So let's say we have, let me give you an analogy. Let's have a whiteboard. When we have a resistor, or let's say 5 ohms, another resistor, 5 ohms, connected in parallel, and we have a current of 1 ampere flowing to this junction. That means 0.5 ampere will move up, whilst another 0.5 ampere will flow through the lower one. And out of this resistor, 0.5 ampere will flow out of this resistor. The same 0.5 will flow out, but when they get to this junction, they will continue their journey as a current of 1 ampere. They continue their journey as a current of 1 ampere. But if we have a resistor of, let's say, 3 ohms, and another resistor, let's say 5 ohms, and current 1 ampere is coming in, I need to remind you that resistance 5 ohms means that its opposition to current flow is greater than the opposition that 3 ohms is giving to current flow. That means that larger amount of current will prefer to come in this direction. So large larger currents, larger I will flow through 3 ohms. Sure that the voltage across them is the same, but the current that flows through them, we are not sure. The current that flows through them depends on the individual resistance, and that is what we have. So, and when we have resistors that are in parallel, there is also a way we can replace these 4 resistors with a single resistance. With a single resistor, we can replace these 4 resistors with a single resistor, and an equivalent resistor that can replace these 4 resistors can be obtained by solving this equation. That is, what is the total resistance for these 4 resistors? That is 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So we do primary school mathematics and we obtain R total. So let's move forward. So this is an example. This example is having resistors R1, R2, and R3, and they have values 2 ohms, 5 ohms, and 10 ohms respectively. So that means that our R1 is 2 ohms, R1 is 2 ohms, R2 is 5 ohms, and R3 is 6 ohms. So I don't think we need a prophet to tell us that these 3 resistors are in parallel. And we don't need another to tell us that these resistors are in series. So a good way to simplify this circuit is to redraw it such that we'll have it in this manner. Where we will say, we'll have it in this manner, where we will say this should be replaced with a single resistor of this nature, while this set of 3 will be replaced by another single resistor. Because when you look at this group, this whole group is in series with this whole group. And that means that we can just replace them in this way. So here we can say that sorry, I think my network fluctuated sort of. Let me go back to share my screen. Come on. While we are waiting for my screen to load, you can go ahead and begin to calculate the total resistance. So that will cover for the time we are currently losing. Okay, so we are back. We're trying to calculate. This is 2 ohms. This is 5 ohms, and this is 10 ohms. The total resistance or the equivalent resistance, a particular resistor that can replace the 3 of them, is 1/2 plus 1/5 plus 1/10. What is LCM? This is the part where you hide your notes from your younger ones. And they see you are still doing LCM and you say you are in the university. So this should be 5 plus 2 plus 1. That is 7, 8. So we have here 8/10. 8/10 is 4/5. So 1/RT is equal to 4/5. That means that RT over 1 is equal to 5/4. 5/4 ohms, or if you like, 1.25 ohms. So in the other scenario, let's use that, those in series, let's use the red ink for them. This is 2 ohms, 5 ohms, 10 ohms. And the total resistance for those in series will be R1 plus R2 plus R3. And that is equal to, this should be 17 ohms. And since the circuit we had earlier is something of this nature, where we said these 2 resistors connected to the battery, where we said this should represent everything here. While this should represent everything here. Let me take this through another route so that there will be no overlap of lines. Good. So that means that we can now come to say the value of this resistor is 1.25 ohm, while this is 17 ohms. Now we are to 1.25 ohms and 17 ohms, they are in series. So we treat them as resistors in series. And for those in series, now the green ones, let's write with green ink. That will be R total of 1.25. Let me make this clearer. 1.25 plus 17 ohms. And that will mean our R total is 18.25 ohms. If you have an objection to that, please let me know. So the total resistance in the circuit (18.25 volts). So, and we are told that 6 volts is, thank you, that 6 volts battery is of negligible internal resistance. So the battery here is 6 volts. What amount of current will pass through the circuit? What amount of current will pass through the circuit? Then we'll remember what Brother Ohms taught us. V equal to IR. And the current we need is V over R, and that is 6 divided by 18.25 ohms. And the overall unit to be ampere. And whatsoever you get is correct. Let's move on. So this is another example. And in doing this, we have to try to look at them carefully. These two are in series. Both of them are in parallel with RB and RC are in series, and both of them are in parallel to RA. R6, 7, 8, and 9 are in parallel to each other. R3, R4, R5 are in parallel. So when we resolve this in parallel, we can now treat it, everything here in series with this and this and this. So I suggest you play with that after the class. I can solve that after the class and post it on the YouTube channel. But I'm not sure if that will be today, but I'll try before the end of the weekend. So let's talk about some circuit laws. We've made mention of them in passing, but let's talk about them directly. So if there are some circuits that you see and you don't even know if the resistors are connected in series again or in parallel, they become so confusing. And Kirchhoff's law is, there are two variants, the current law and the voltage law. So the current law tells us that the current that enters a junction is equal to the current that leaves the junction. So this is this figure, or you look at this figure, the arrow shows you the direction of current flow. So the current is entering the junction and some other currents are leaving the junction. So it's just like a pipe of water entering a junction with 3 different ends. The amount of water that enters that junction is equal to the summation of the amount of water that leaves the junction. So a way to talk about it in algebra is to say that the amount of water, the sum of water, or the algebraic sum of water entering that junction of your water pipe is 0. Similarly, in electricity, we can say that the algebraic sum of currents entering a node is 0, because the currents entering the node, we have taken it to be positive, and the current leaving the node, we have taken them to be negative. Then we can say the algebraic sum of currents entering is entering that node or entering that junction is 0. Well, Kirchhoff's voltage law tells us that the algebraic sum of voltages in a closed loop is equal to 0. The algebraic sum of voltages in a closed loop is equal to 0. So this is like a consequence of Ohm's law. It's a consequence of Ohm's law, where we have a voltage source and we have resistors. We have voltage source and we have resistors, and current is flowing through the resistors. What we have learned earlier from Ohm's law tells us that resistor R1, R2, R3, they are in series. The same current I will flow through R1 and R2 and R3. So, but what we did not mention is the voltage drop as the current is flowing. So as current is flowing through the resistors, voltage drops. When we say this, for instance, to be let's call this to be a 9 volts battery, and let's call this R1 to be a 1 ohm resistor, and let's say R2 to be okay, let's make it even. Let's say this is 3 ohms resistor 3 ohms resistor, and 3 ohms resistor. So they add up to give a total resistance of 9 ohms. When you connect this to the battery, you would expect that a current of 1 ampere will flow out of the battery. When a current of I equal to 1 ampere flows out of the battery, current 1 ampere will flow through R1, and the voltage of 3 volts will be across R1. The same current I1 will flow through this R2, and a voltage of 3 volts will be across R2. The same current 1 ampere would flow through R3, and the voltage drop 3 volts will be across it. So when you add the 3 volts here to 3 volts here to 3 volts here, we have 9 volts. But in the 3 volts we have added here, the 3 volts here is IR1. The 3 volts here is IR2. The 3 volts here is IR3. So when you add IR1 to IR2 to IR3, you should get V, which is the voltage supplied to that loop. But to now think about it in an algebraic manner, we are going to say that the algebraic sum of the voltages in the loop equal to 0. That will take the supply voltage to be positive, and the voltage across the loads, the voltages across the resistors, will take them to be negative. In that manner, we'll be able to say that then our V, we'll be able to say that our V minus IR1 minus IR2 minus IR3 equal to 0. So these are the two beautiful laws from Kirchhoff that will save us from a whole lot of embarrassments very soon. Now look at this figure. We have resistors R1, we have resistors R2, R2 and resistors R3. Then my question will be, R1 and R2, are they in series or in parallel? R1 and R3, are they in series or in parallel? For you to say two resistors are in parallel, their ends must connect. Both ends must connect together. This is the requirement for being in parallel. R1, the right end of R1 must connect to the right end of R2. The left end of R1 must connect to the left end of R2. That is how you can say they are in parallel. But when you look at these resistors, how do you resolve them? How do you say, I want to make these two in series so that I will know the current flow, and I want to put those two in parallel to know the current flow? So this problem can be very embarrassing. Thank God for Kirchhoff's law. So we are applying the two Kirchhoff's laws, which are the Kirchhoff's current law and the Kirchhoff's voltage law. The Kirchhoff's current law tells us that the algebraic sum of current entering a node is 0. And this problem is already half solved because we've been provided with the direction of currents I1, I2, and I3. So that means that when you look at this, it tells us this I1 that is flowing here is the I1 that will flow through this channel until it gets here. I2, which is here, will flow from this point here. While I3 is the current that will flow through this channel, I3. So I3 will flow through this resistor and split into two. So split back into I1 and split back into I2. So we can now say that I3 is equal to I1 plus I2, because I1 and I2 are flowing into this junction 2, adding up to give I3 to flow downwards. So easily we can say I3 is equal to can say I3 is equal to I1 plus I2. And if you want to talk like our friends from mathematics that do algebra, I3 minus I1 minus I2 equal to 0. We are saying the same thing. So now let's now apply current. So what we've just done is we have applied Kirchhoff's current law. So now let's apply Kirchhoff's voltage law on the both loops. For in loop A, we can see that we have chosen this to be a direction of navigation, while for loop B, we're taking this to be a direction of navigation. So for the fact that our direction agrees with the direction with which I will expect current to flow out of this battery, then I will say 15 volts. And the other point is to know that the direction with which current is flowing out of this R1, the direction with which current is flowing through this R1, that is I1, the direction with which I1 is flowing through R1 agrees with this our loop. Then I will say minus 4I1. And why do I have minus 4I1? Why do I have 4I1? Because the voltage drop across R1 is 4 times I1. That is 4I1. V equal to IR, voltage, current times resistance. I is I1 and R is 4. Then coming to this resistor R3, because we are interested in just this loop. In this resistor R3, the current flow is I3, and the direction of that current flows agrees with the direction of our loop. And I will still continue to say minus 2I3. Then I'm through with the loop A. Then coming to loop B, we have chosen to travel in this direction, in the anti-clockwise direction. And looking at this 12 volts battery, that will oppose the direction of current flow. Okay, sorry, it agrees with current flow. We expect current to flow out of the 12 volts battery in this direction, which agrees with the direction of our loop B. So similarly, we can have 12 volts. And we also consider the direction of this loop. It still agrees with the way with which I2 will flow through R2. Because I2, R2 will be a voltage drop, then we say minus 3 I2. I2 flows through R2. So, and R2 is 3. Then 3 times I2 is the voltage drop across R2. Then coming to R3, we would have I3 flowing through R3. Then, since the direction of current flow still agrees with the direction with which we navigate that loop, then we'll still stay minus again. And that will be minus, it's 2 ohms times I3. So what we do next is that we replace the both I3s here. We replace both I3s here with I1 plus I2. Because I3 is equal to I1 plus I2, so we replace both I3s with I1 plus I2. By doing that, we will have an expression that has 15 volts and just I1 and I2. Then we solve simultaneously to obtain I1 and I2. separately. So I'll put some other examples on the YouTube channel. I've posted the YouTube channel on the LMS page. You can go there and look at view the previous videos of previous class lectures and some other videos in which that emanated from our students asking some questions. So the time is up, so we'll continue on Monday. Have a nice weekend. Bye.